pulse induced magnetization dynamics and reversal of magnetic field. So, yes, Dr. Kaushalya, you can please start the talk.
Hello, am I audible?
Yes, you are audible.
Okay. Thank you so much, Neil ma'am, for the introduction. So let me just get the pointer first. Okay, hello everyone. My name is Kaushalya, as you know, and today I'll be talking about ultrafast manipulation of magnetization using on-chip terahertz or picosecond wide electrical pulses. Okay, so this is the outline of my presentation. So I'll walk you first through the introduction and the motivation part of the study, and then the methodology where we will discuss about the fabrication of these on-chip terahertz devices we're going to be using, and also the characterization for probing the dynamics, and finally the results. The main result is basically the picosecond spin orbital driven magnetization reversal in a cobalt ferromagnet by using a single 6 picosecond wide electrical pulse. And finally, the conclusions. So let's start with the introduction. And since the speakers before me have already extensively discussed the introduction part, so I'll just go quickly through it. Okay, so as we all know that hard disk drive is a classic example of a spintronic device. One of the recent device is MRAM. And basically in both these devices or in general, in any spintronic device, we perform two different operations in order to store and read the magnetic information or the information in general. And we do these reading and writing operations in the binary form, meaning in ones and zeros. So here in my talk today, I'll be mostly focusing on the writing operation, and I'll be switching between the writing word and the reversal magnetization reversal, and it will mean the same. Basically, the idea is that in order to write information, you need to have a very good control over the magnetic state of the magnetic bit. And how can you do that? By using different mechanisms. So for example, the first approach or the most conventional approach is to use the external magnetic fields, but as we all know that it's not an energy efficient approach. Now the second approach is to use spin current pulses. It's definitely a promising approach in terms of integration because it's easy to integrate with the existing electronics. But the switching speed so far has been limited in the range of few hundreds of picoseconds. Now, the other approach can be you directly shine the femtosecond laser light on your material. And of course, using this approach, the switching will be faster. But then the limitation is that not every material shows this kind of so-called all optical magnetization switching. And also when it comes to integrating the laser with the existing electronics, it becomes tricky. So here lies the idea, and that is to basically combine both these approaches in order to take benefit from them and get rid of the drawbacks. So we're going to be using spin current pulses, but ultra shorts in order to make the whole process faster. So we're going to combine that. But before getting into the approach, I will first go through how do we use the spin current in conventional ways for the magnetization reversal. So one way is to use spin transfer torque, where we have this soft ferromagnet and hard ferromagnet sandwich structure. And then we use this hard ferromagnet in order to basically spin polarize the charge current, and then finally apply the torque on the soft ferromagnet in order to switch its magnetic orientation. I don't have to go through the weak points of this approach, and we all know that spin orbit torque is more promising approach. So in spin orbit torque, what we do is we take the heavy metal instead of a ferromagnet in order to spin polarize the current, and then basically when we put the ferromagnet on top of this heavy metal, we get this torque called spin orbit torque, and that torque can basically do the same perform the same operation, that is to flip the magnetization of the ferromagnet. Now here, the challenge is that we would like to do the switching as fast as possible. And one of the parameters that governs the switching speed is the pulse duration of the charge pulse we are using. The shorter the charge pulse we use, the faster the switching will be. Of course, it is also limited by the internal property of the magnet we are using, but within the limits, it works. So now the limitation is that we need to have these short electrical pulses. But just to give you the context, right now in the market, there is hardly any pulse generator available that can provide pulses down to, let's say, tens of picoseconds. And the pulses we're going to be using will be in a single digit, so single digit picosecond electrical pulses. So we'll see how do we generate them. So it's just a reminder slide that we're going to be working somewhere in between the classical spintronics and the optomagnetism, and we're going to be using terahertz electrical pulses. In order for today, we will be focusing on the reversal of a ferromagnet using spin orbit torques at picosecond time scales. And for that, we will go through different steps. So terahertz generation, then detection, and finally, we will integrate them with the spintronics in order to perform the desired operation. So with that, we switch to the methodology section. And here, for the terahertz generation, we are using the photoconductive Austin switches. And the way it works is that when you shine intense femtosecond laser pulse on this semiconducting material, you create electron hole pairs, and these electron hole pairs, further in the presence of external electric field, get accelerated and give the terahertz pulses. And the reason why we were also interested into using this particular approach was the pulse duration. We can get very short electrical pulses by using a promising material that is low temperature gallium arsenide. And we can also get intense and unipolar terahertz pulses with this approach. Now with that, we move to the terahertz detection. And for detection, here what you see is one of the device under the microscope. And here this is the terahertz emitter, the photoconductive switch. And for detection, we are also using a very similar type of Austin switch. But here, instead of using it as an terahertz emitter, we use it as an antenna in order to probe or detect the terahertz electric field. And basically using the delayed the pump probe setup, basically we can get the time resolved electric field component of the generated terahertz pulses anywhere on the transmission line. And by performing this kind of measurements, we can of course know the pulse duration of the generated pulse and also the losses and also the propagation speed, as we already know the dimension of our transmission line, so we can back calculate that. For the moment, the amplitude is not well calibrated, but the work is underway, and very soon we'll have exact value of the peak amplitude of the electrical pulse we are generating. So, so far we have seen terahertz generation and detection. Now let's move to the final section, that is to integrate these terahertz pulses with spintronics or different magnetic nanostructures. And in order to do that, we work with this kind of on-chip terahertz device. And so here we have in one side our photoconductive Austin switch. When we shine it with femtosecond light, we get the terahertz. And then for propagating this terahertz and let it reach to the desired magnet, we use different transmission line structures. For example, here we are using coplanar waveguide. So the terahertz can travel through it and reach all the way to the magnet. And we can basically put this magnet at a desired position depending on the operation we want to perform. So here is the magnet, the photo switch. This is basically the terahertz electric field we have detected on this kind of device. And now the question will be, how do we probe the magnetic response after the terahertz magnet interaction? So for that, we use another femtosecond low intensity pulse, which we call as probe pulse. And when we provide delay between pump and the probe pulse, we can get the time resolved magnetic response of the magnet. And we will discuss that later on as well. And we can also do it with Mach microscopy, and we'll see that. So now the question is, how do we fabricate them? So for fabrication of these kind of devices, it's pretty straightforward actually. It's a three-step lithography-based device, and here you can see that on a single chip of 1 centimeter cross 1 centimeter, we can have 6 different devices with different photoconductive switch parameters and sorry, and the transmission line structure. So after the fabrication, let's now move ahead with the characterization. So for characterization, we developed this MOC setup. So it's a conventional static MOC, as you can see. So here what we do is basically shine the light on the material and then probe or detect the magnetic response of the material by detecting the reflected light, right? And we do it by measuring the change in polarization. And for that, we have to use the pair of analyzer and polarizer here. And in order to get better signal to noise, we are using the lock-in detection. So as we know that, okay, we can get this kind of hysteresis loop with the static MOC, which gives us the information about the point on the point about the information where you shine your, like where the laser spot is on the sample. But if you want the spatial resolution, we can use MOC microscopy. So we can bring a microscope over here along with a pair of polarizing analyzer, of course, in order to have the sensitivity. And then we can basically see that we can probe the magnetic response, and we can see the domain formation and etc. So now that we know how to probe the static magnetic properties, our ultimate target is actually more than that, and that is to probe the ultrafast dynamics. And in order to do that, we need to have time resolution in the range of femtoseconds to picoseconds. And in order to get that, we have basically used the pump probe setup. So the addition in this pre-existing setup is basically another femtosecond intense laser beam, which we call pump beam, and along with the delay line, we can basically provide delay between the probe and the pump, and hence we can get the time resolution. So these are some of the parameters for this particular setup at this moment, and this is how the actual setup looks like. So here on the setup, we can have in plane and out of plane field here all the way up to around 200 millitesla. And so now when it comes to what kind of different like measurements we can do, so the one of the simplest measurement is the so-called all optical measurement, where we pump the magnet directly with the femtosecond laser light and also probe it with a low intensity probe femtosecond laser pulse. Now we can bring the pump beam on the photo switch, and now we can pump the magnet by terahertz instead of the femtosecond laser pulse. And this kind of measurement we call as electro-optical measurements. And the third type of measurement is all electrical measurement, where we basically pump, or not just pump, but generate the electrical terahertz pulse and then again detect them electrically. So, all right. So now we know how to fabricate devices, how to characterize them. Let's do something. So, and that is to try to reverse the magnetization of a ferromagnet at picosecond time scale. And for that, we decided to work with this specific magnetic stack over here. So here the ferromagnet is a 1 nanometer cobalt with the PMA, meaning the spins are pointing out of the plane with respect to the sample plane. And then we have the platinum and the tantalum as the buffer and the capping layer. and the heavy metals that are actually being used for this spin orbit torque are basically this bottom 4 nanometer platinum and top tantalum layers. And as we know that the spin Hall angle for tantalum and platinum is opposite to one another. So the idea was basically to enhance the overall spin orbit torque that is acting on the cobalt. Now we also had to introduce this very thin 1 nanometer copper layer in order to reduce the DMI and uh, make sure that we do have PMA plus two very distinct remnant states. And when we did not have this, we were not basically having very distinct two remnant states. All right, so once we were satisfied with what kind of stack we want to work with, we decided to check if this kind of stack is working for the conventional spin orbit torque studies. So we patterned this structure in the whole bar geometry, and then we did this kind of hysteresis loop by basically changing the relative polarity between the external in-plane field Hx and the electrical current. And we did see that indeed in our stack the SOT symmetry is working, and the way it was such that when you apply the current and the external in-plane field Hx in the same direction, you get minus mz as your final magnetic state, and when you reverse the polarity or when they are anti-parallel to one another, it is positive mz. Now that we know that the spin orbit torque at conventional with conventional method or wide electrical pulses works, now we can check if it works at picosecond time scale. So to check that, we basically deposited this particular magnetic stack here at the place of the magnet, and then to detect if we are being able to reverse the magnetization of this magnet, we use smoke microscopy. So here are these two different saturated states. So we basically apply external magnetic field and made sure that the magnet is saturated. So the gray color after the background subtraction represents the minus mz state, and the black curve, color over here represents the plus mz state of the magnet. So then we shine the switch with the femtosecond light. We get the terahertz pulse. And now the question is, what happens when you bring a single 6 picosecond wide electrical pulse to this magnetic structure? Okay, so this is what we get. For a threshold value of 40 volts bias over here, and a particular value of pump power, we get the full magnetization reversal of this cobalt ferromagnet just by injecting a single 6 picosecond wide electrical pulse. So of course it was pretty satisfying to see these results, but then the question is it really a spin orbit torque driven magnetization reversal? And to prove that, I'm going to show you the results in 4 different quadrants based on the combination of polarities of the applied electrical current, the pulse, and the external in-plane field Hx. So we know what to expect from the conventional spin orbit torque measurements, but now let's see what happens here. So we'll start with initial state. So we saturate our magnet in negative mz direction, and then we bring the picosecond pulse, and we saw that the magnet switch. Now what we can check is we keep the initial magnetic state at positive mz, and we apply the same electrical pulse with the same combination of polarities. And this is what we get. So basically, we verified that the final magnetic state of this magnet was fully determined by the combination of the I and the Hx we were using, and which goes very well with the spin orbit torque symmetry. Now, in the rest of the quadrants, we just further verify that the symmetry holds. So here, as you can see, the I and Hx polarities are now parallel to one another, and we know that for parallel case, the final magnetic state should be negative mz. So we should only see gray here, and which is indeed the case. And similarly, it was as what we were expecting for rest of the symmetries as well. Now, after this, we further verify the same spin orbit symmetry by using a slightly different device. So here, instead of using the coplanar waveguide, we use coplanar strip line. And the interesting part about this device is that we have the magnet both on the ground and the signal lines. And having that, it gives basically different polarities for the ground and the signal. So what we can expect eventually is that the spin orbit torque should also be applied in the opposite direction for both those lines. And the final magnetic state after the pulse arrival should be different. And let's see if it holds. So basically, this is the saturation state. So we can start from negative MZ or positive MZ for both the ground and the signal lines. And the final magnetic state was indeed opposite for both these lines. So it again verifies the spin orbit oximetry. So it's pretty cool. But now the question is how exactly the magnetization is responding at these ultra short time scales. And in order to know that, we perform time-resolved Moog measurements. So let's see. So let's start first with the initial saturation state. So we saturated our magnet in, let's say, positive Z direction. So the anisotropy, the effective field, and the magnetization is pointing towards positive Z. And now when we bring our picosecond electrical pulse, depending on the polarity, we can basically tilt the magnetization towards positive or the negative Y direction. And corresponding to the situation, we get this kind of response. And this response is basically a combination of this picosecond spin orbit torque and also the ultrafast demagnetization, which will be also acting because of the intense terahertz electrical field. And I don't really have to explain this because speakers before me have already explained the ultrafast demagnetization. So now here the interesting part is that like we are kicking the magnetization with the spin orbit torque. So ideally it is going to start precessing, but we don't see any kind of precessions here. And the reason is because the precession is happening in the plane. And if we want to see them, or basically reverse also, we need to have some applied like this external in-plane field in order to basically slightly shift the plane of the precession by changing the H effective. So if we do that, we can see these precessions. Now we can verify the symmetries by changing the polarity of, let's say, one of the components. So going from the red curve to the blue curve, what we are changing is the polarity of the external in-plane field. And we can see that now it is going in the other direction. We can further clarify it or verify it by changing the polarity, and we can see that indeed it holds this spin orbit torque symmetries. Now again we verify by starting the magnet at negative MZ saturation, and we get these beautiful results, which basically holds the spin orbit torque symmetry. Indeed, these measurements were not at the switching threshold, so we are not completely switching the magnet, but the red curves you are seeing here are the situations where we are actually providing the combination of I and HX in such a way that we flip from one magnetic orientation to another magnetic orientation. To best of our knowledge, this was the first time when ultrafast heating along with ultrafast spin orbit torque was reported. Now, after the experiments, we wanted to check what the macrospin model is predicting. So,
Suchita, sorry to interrupt, but uh, please try
hello.
to wrap up. We are running out of time, so maybe
Okay,
please
sure,
you can try to
sure,
wrap up the talk.
sure,
Yeah.
sure, sure, sure. Just 2 minutes.
Yes,
Okay,
yes.
so basically for the simulation, we use this simple LLG equation. I can be actually quick. So what we did is this LLG equation with fill-like and the damping-like term, and the SOT term, along with some thermal contribution, because the fact that the terahertz pulse was intense enough. So when we take all the thermal contributions into account, we can get this kind of fits. So which this is not the perfect fit, but still pretty good considering the fact that it's a very simple microspin model that we used. Okay, and here I would just like to uh, like say that there was something in addition that was acting in order to basically reverse the magnetization at these short time scales, and the sorry, I lost my flow after that. Okay, I need to regain. So it was thermal anisotropy torque. So the fact that the picosecond electrical pulse is intense, it basically provides or heat up the magnet, and hence the magnet the anisotropy goes down. Okay, I think I need to I need to skip this for now. So okay. Just to conclude, I have showed you the on-chip terahertz device fabrication and characterization, and this unique pump probe tool, terahertz generation and detection, and finally and the applications. So the time resolved picosecond spin orbit of dynamics and the reversal. I would like to acknowledge my PhD advisors, our collaborators, and my Spintronics team from France. Thank you so much for your attention.
Thank you so much for the interesting result. And,
Sorry, I messed it up in the in the
it's
end.
okay. So, Pranab sir has a question. Sir, please.
Hello,
Sure.
Kaushalya, very good indeed. I have seen this paper also.
Mm-hmm.
So, in the last part, when you talk about SOT switching,
Yeah.
so you are saying that the switching is very fast, or it is the demagnetization which is fast? I could not.
The switching. So basically, it's here the demagnetization is definitely there because the terahertz pulse is intense enough. So the demag is there, but the spin orbit torque itself is very fast because the pulse is very short.
Because the SOT switching was studied by this Petriog umbrella group, So
Yeah.
there it was in nanoseconds. Of course, those are all electrical.
Yes. Yes.
And there was also some kind of delay there. So you do not seem to see any of those phenomena in your data. So I
Yeah.
was. Mm.
So when you are saying delay, like which delay you are talking about is the delay when the SOT start acting on the magnet. That's the delay you are saying? Because
Yeah,
if you are saying,
in their case,
yeah,
it was a current induced, so the current was
yeah,
passed, and they're sending a pulse, and then
yeah,
it doesn't switch immediately. So after the
yeah,
pulse is on, then it took some
mhm,
time for the magnetization to respond.
yeah.
Mm.
Yeah, and here you can see in our study, we can really see that the SOT is instantly acting on it. So it's pretty fast. So
Uh,
this is basically like if you see the red and the blue curve, it's basically the contribution from the SOT that is like that wants to go in one direction, but when you flip or change the direction of external plane field, the precision wants to go in the other direction. So it is actually a sign of the SOT that is acting at a very like it's very fast and instant.
yeah, yeah, yeah,
Yeah.
yeah. Okay, thank
Oh,
you. Mm.
so,
Thank you.
Professor Bhagwati can also go ahead with the question. We will take it quickly.
Hi, Kaushalya. This is Bhagwati. Yeah. Just wondering, how much, like in terms of the current density, when you use the laser with the current, how much current density you reduced with this combination compared to the
So
without laser?
yeah. So actually, to answer that question, because of the fact that we do not have the exact value of the current of that is there with our terahertz pulse, so we don't have the exact value. but we try to estimate the energy by checking the capacitance, or hence the maximum energy this photo switch can store and hence provide to us. So if we try to calculate that, then this is the basically the current densities we get. So it's like 6 × 10⁻12 ampere per meter square. And if we like back calculate it, then it's like I think it was around 20 picojoule for to reverse like a 20 nanometer square area. It was
Okay,
about that.
good.
Yeah.
And how nicely you can focus this laser within what is the lowest what is the resolution you have?
So the
Like,
probe size was 1 micrometer.
okay, so can we not do in
Yeah.
like 2 nanometer like range?
I think that's the
So you
limitation with the lasers, right?
with the laser, there is something called hammer, heat assisted media recording. They also do
Yeah.
something similar. They apply the heat with the laser in
Hmm.
individual bits, so they increase the temperature of individual bit, and then
Yeah.
they switch it at lower magnetic field. So it's something similar here you're doing basically, am I right? Like with the
Okay.
laser you are heating up, but then you are reducing you need a less
Yes,
current to switch it, and then you can do fast,
exactly.
both of them fast.
I
Yeah,
Yeah.
actually,
think we can discuss this further in the chat, and
Okay.
we can
Okay.
take
Sure.
one quick question from Sandeep because he has been, I think, waiting
Hello.
for quite a long time.
Yeah, hello.
sure, sure,
Hi.
sure.
San,
Yeah.
Hi, ma'am. Am I audible?
Yeah, you are audible.
yes, Sandeep,
Ma'am,
go ahead.
my question is I have a basic question.
Mhm.
Terahertz pulse have associated magnetic field also component. So, do you want to comment on that? How it is affecting that magnetization dynamics and
Mhm.
magnetization reversal and all these
Okay,
things?
so yeah, so from what I understand is like uh, like when you start propagating your terahertz pulse in these different transmission lines, so now you can think of it as combination of electric field and the magnetic field, right? And how the Oersted field is distributed. So the reason why we also like try to check both with the coplanar strip line and the coplanar waveguide was just to make sure that there is no contribution from the I would not say no contribution, but there is no significant contribution at least from the Oersted field. So for example, we made sure that when we are using coplanar waveguide, since the geometry is symmetric, so the Oersted field between this upper ground and signal line and the lower ground and signal line is basically canceling each other. So we are not ending up providing any additional Oersted field via the terahertz directly.
Okay.
Uh, does that answer your question? Like my point here is
Yeah.
that we are not we don't need to worry about the field that is there with the terahertz. Indeed, there will be because we need
Electric
that
field,
field
the
for the
electric field is high enough, then associated magnetic field can
yeah
significantly change the magnetization dynamics and
yeah
magnetization switching.
yeah
So,
yeah yeah.
it's
But
okay.
the fact that the symmetry is there
Okay.
on the devices, so it basically cancels out.
Okay.
And the magnet that is here at the center will not experience that Oersted field.
Okay. Thank
Yeah.
Okay, Sajid was supposed to ask a question. Please use the chat, Sajid, if you are comfortable.
Okay, okay,
I'll
okay.
suggest that. And we now will have the last talk of this workshop, as well as uh, for the uh, for the session. So this will be by Professor Bhagwati Prasad. He is an assistant professor in the Department of Materials Engineering at the Indian Institute of Science, Bangalore. Currently, he is working on emerging memory technologies for the Internet of Things and artificial intelligence. Before joining ISC, he worked as principal research scientist at Western Digital